Good afternoon. This is Mitch McMurray. We're here for chapter 27, Plate Tectonics, Continental Drift, and a few other things like that. Okay, C4 spreading and other stuff. All right. So basically, we've talked a little bit about what the structure of the Earth is and how we know that from the earthquakes and so forth. Um, Today we're just going to talk a little bit about plate tectonics. Now we're mostly going to hit the high points. Unfortunately, I can't take you underground and show you exactly how the plate tectonics work, or to a scene of active volcanism where things are being subducted or magma is being spewed out. I would like to be there, but no. Okay, so what we're going to talk about first of all, continental drift. Continental drift is not the same as plate tectonics. Continental drift was an idea advanced early on that planets around World War One, 1915, thereabouts, that plates that we talked about, the lithosphere that we talked about last chapter, floating up on top of the asthenosphere, okay, these plates floated or moved and had drifted, and therefore the continents had not been always in the same place that they are now. Okay, the idea was brought up by a German scientist, Alfred Wegener. At the time, it was not really accepted very much, partly because he had his thumb in a lot of pies. He was a meteorologist, he's a geologist, he had a lot of different background and meteorologists and all these different things, particularly meteorologists, which is weather. And so when he came up with these ideas that really was trying to revolutionize the way people thought about the Earth and geology, a lot of people didn't give him much credit. But actually, as time has gone on, we have found some things that have proved that in general, he was on the right track and was more correct. And so he was actually very creative. And it kind of shows in science you have generalists and specialists. Sometimes someone specializes in one area, and so they do really good work in that area. But also, sometimes people who have knowledge from a wide range of different subjects are able to put what they know from, say, meteorology and paleontology, fossils, and stuff like that, and geology, and put it all together because they know a little bit about all these different fields. And as a generalist, they can see how they interact with each other. And that's kind of what happened with Wegener. He could see all these different things that pointed toward the fact that the continents may not have always been where they are now. And he called that theory continental drift. Okay. Now, what are some of the things that Wegener came up with? Okay. Well, first of all, as soon as they first maps came out many, many years ago, people noticed how a lot of North and South America seemed like they would fit into Africa and Europe. For example, Brazil, where it comes out here, looks like it would fit right in there on South America. This top part of Africa here looks like it could kind of fit in right there in the Gulf of Mexico, sort of. Okay, Greenland could have been squeezed and compressed back down here into Canada and the rest of North America, and you can kind of see how Europe could fit in there, and you certainly could have put Antarctica somewhere down here or Australia up in here. Okay, there was a certain thing where it just that looked like they kind of fit together like a jigsaw puzzle, but unfortunately, that's not very good proof. That's just yeah, neat idea. But the question was, continents don't move. Obviously, you look at the ground; it stays still, it's solid. That's what we talk about being on solid ground. Okay, so they don't do too much. So, but it did notice that they really aligned up here. Now, it turns out that scientists noticed that if you go out here, there's a continental shelf where it's fairly flat and then it drops off. And that continental shelf, if you look at the lines of the continental shelf and compare it to the coastlines, they even fit even better than the actual coastline. Here's where the actual coastline, but if you looked where the continental shelf was on the side, on this picture they have added the continental shelves, that they fit even more exactly kind of together, could fit together. And so there was always this idea that the continents looked like they could have fit together at one time, but no one could really explain why. The other thing, though, they started finding out some things. They started looking at the rocks, look at a lot of the rocks in North America and Europe and South America and Africa. Um, a lot of them were very similar. Had the same kind of layers, same kind of fossils in them, and so forth. And they said that there's a lot of similarities in these mountain ranges, even though they're separated by an ocean now. Okay, and so the idea was at one time they might have been the same ocean range. Of course, another thing is fossils. All right, they began discovering fossils. Um, see if I have that. All right. several kinds of fossils were found in several areas that were widely separated by oceans now. And had they been separated when these continents were, when these animals and organisms were alive, it doesn't really make sense. Some of them, for example, were land-dwelling mammals, not the type to go swim across an ocean or somewhere and too big to be carried by the wind or some such thing like that. Trees and plants that were found in places like um, South America, Africa, Asia, Antarctica, Australia, and these places are all widely separated. So how could they have possibly had these same fossils? Well, the idea was if these were all once together in a similar place, okay. So for example, like this, and say Australia was in here somewhere, and Antarctica were somewhere up here, then that would explain where they could be. Also, some of these places, like if they were found in Antarctica, which now is the South Pole, extremely cold, which indicated that maybe at one time Antarctica was either, you have to think the South Pole was occasionally at one time was a tropical forest, swampy forest, or maybe Antarctica has moved from where it currently is. All right. And that kind of goes in the last one we'll call the paleoclimatic data, which just means what the climate was like a long, long time ago. And that's kind of what, if you find peat, bog, swampy fossils in Antarctica, then obviously, and at the same time, when you find those in the same age rocks, much of the northern hemisphere is um, tropical, which are now far north, and some of these, like Antarctica is far south now. But at one time, they had more tropical type climates, and it's kind of hard to explain how that could have been given their current locations, unless you think the whole Earth has totally tilted or something like that, and there's really no evidence of that. So you find records in the rocks of glaciers, the way they scrape or leave striations across the rock and grind up rock. We don't really relate to that a whole lot here in Texas because we're lucky if we get a little bit of ice and snow every year. But there's signs of glaciers in South America, Africa, places like that that obviously aren't that cold now. So it's possible there was a whole different ice age, but also it's possible that their location has changed, and that one time maybe they were more closer to the poles or something of that sort. So there's a lot of evidence here. Now the problem was Wegener did, especially for his day and age, did a great job of giving evidence and saying these are things that all point toward the fact that at one time um, they might have all been connected. Okay, and he gave his theory the name continental drift because he says, well, these continents have been drifting or moving over time. Okay, now I said it wasn't real widely accepted. Well, one, it was the middle of World War One, so there were a few things going on in other people's minds. He was primarily a meteorologist, not a geologist, and so people thought, oh, this is kind of crazy. Um, he eventually, just for the record, died in Greenland, on an expedition to explore up there, and technically is still there as far as we know. Never returned, and so probably in an ice sheet somewhere, which I don't know if he would be happy about that or not, but there you go. But the main problem was he could not explain how these continents could move around because there's no really explanation for that. He had some ideas that maybe like the tide pulls on the moon, pulls on the oceans, maybe something like that happened with the continents. Maybe the continents were like icebreakers, the ships that go at the North Pole and just cut through the um, um, ice and break things loose. Maybe that's what the continents were doing. They were just swimming through the ocean, breaking up the continents, and they're moving different places. But he really didn't have any way to explain what was making this happen. How could you explain how these uh, continents can move around? Okay. All right. So that was kind of his idea. And that's kind of where it left it for a long time. People kind of debated it back and forth, but it wasn't until probably in the 1940s and 50s that it started coming along and people started doing it, okay? And because we found out some things that started making more sense. One was a man named Harry Hess. He was, I believe, at Harvard or Princeton. I can't remember for sure. Give him back credit. But anyhow, during World War II, he was on a ship and he was stationed on the ship. And part of his job was to, they were trying to map the bottom, see how deep um, the ocean was for navigation purposes and also checking for where submarines and things like that might hide and so forth. And so instead of just turning it off and just only doing it when they really wanted to check something out, he kind of left it on all the time and said, hey, let's just check out what the whole bottom looked like. And one of the first things he noticed, we assumed that the ocean was like a lake. You know, as you get farther out, it gets deeper and deeper, and then it would be deepest out in the middle. But what they actually found in the Atlantic Ocean is as you go out toward the middle, there's this mountain ridge running down the middle of it. And so it's actually fairly shallow there. And in some other places, especially in the Pacific and other places, there were actually where there was deep, deep trenches, and they were usually relatively close to the continents rather than out in the middle of the ocean. Okay, and so this one definitely changed the way people looked at the ocean. And as he looked in these mountain ranges in the middle, uh, it says in the middle of the ridge, there's a volcanic rift going down the middle of it. Okay, and so it's almost a rift is where when it pulls apart, and so now you've got this deep spot in the middle. It's on this mountain range, but then there's a rift in the middle of it as if things were pulling apart. Okay, and so these were kind of interesting. It certainly told them a lot more about the ocean that wasn't like they thought. It tended to show that it was um, not the structure that they thought. It definitely wasn't just like a big lake where it just gets deeper and deeper out in the middle. It was actually deeper in some places near the continents, and out in the middle you had this long mountain range, basically running up the middle of the Atlantic Ocean. Okay, very massive. In fact, technically, it is the longest mountain range in the world underwater, granted, but just like some of the canyons and stuff like that, or and mountains, some of the biggest, tallest mountains technically on Earth are the islands that are sticking out because they come all the way from the base of the ocean all the way up. But anyhow, now another thing that happened is as they started studying these, they took rock samples from here and found that the magnetic fields, if you had magma, which would be what would make these volcanic rifts, okay, the rifts pull apart, magma comes up, it's liquid. And in there, you have a certain amount of magnetite and some of these other magnetic minerals that we talked about. And what they found is that the magnetic minerals in one rock would be lined up one direction, and then they might be lined up in a different direction in the next layer. Okay, and as they dated these with radiometric dating, remember we talked about radiometric dating where you take the amount of isotopes of, say, uranium and how much of it has changed into lead, and you calculate the age, they found that all these rocks were not the same age. These different rock layers right here were not the same age. So there's different ages. So kind of like as it pull apart, magma would come up, harden, turn into rock, but then it would split apart. And so you had these layers as they got older as you got far away from the ridge in the middle because they had been put there longer. And because they had formed at different times, the magnetic minerals like magnetite had lined up in different directions. Okay, and why were they in different directions? Well, one possibility, of course, is that these plates were moving over time, and so that would require them to line up in different directions. Okay, that could also be possible that we said the magnetic field of the Earth is caused by that outer core, the movement of that outer core that creates the magnetic field. It could have changed its movement as well. But one idea is that the continents were in different places. But at any rate, definitely all these different layers of rocks were different ages, with the newest rocks right down the middle and the older rocks as you get farther away. But in general, ocean crust tended to be newer than continental crust. Okay, because the continents we think have basically been there for quite a while. All right, but we have this new ocean crust being created, so many of this crust, oceanic crust, is relatively new. All right, now. What we also want to find out is that we did this. Hess looked at this and said, okay, I've mapped this area, I've seen these different layers. He came up with an idea he calls seafloor spreading. Okay, and basically this was the idea that new ocean floor is being created where this is pulling apart. So I said, well, okay, that's great, but why are there not? Why isn't the Earth getting bigger then? If you get this crust spreading apart and getting bigger. Basically, he said that somewhere else where we have trenches, we have crust coming together and they're crumbling and going down, being pushed down into the earth where they begin to melt and be recycled. And so basically, he's saying for every part on the earth where you have these ridges where new crust is being laid out, somewhere else these plates are coming together and being subducted or going down. That's why you have the trench, because as they cool down, you've got these really deep trenches, okay? And so basically, the size of the Earth is remaining the same. The amount of ocean crust is remaining the same. We have new crust being built in some areas, but you also have old crust being destroyed and turned back to magma at other places. All right. Now, he proposed that this is basically caused by convection currents in the mantle, okay? This is kind of going with what we were learning about what we think about the inside of the Earth. We talked about last time, you have those convection currents. So as they move, I don't know if we have any of that pictures like that. No, probably not. Probably in the last chapter. But as the magma and the liquidish rock in the asthenosphere, that upper layer of the mantle, as it moves, if they're moving this direction, the current's going this way, that pulls it apart, which is what would be happening here to mid-ocean ridge. Okay, you have going this direction and this direction, that's pulling it apart. Other areas where you're being subducted, the convection currents are bringing them together. That's where they're crashing into each other and then having to be pulled down. Now, so this was the idea of seafloor spreading, which kind of explained the mechanics behind how the idea of continental drift could have occurred. So this really strengthened and brought people back to Wegener's ideas that he'd come up with 50 or 60 years before, but had largely not been accepted. Okay, and so they kind of put these together and they said, hey, let's go with a new theory that kind of brings all this together. Okay, and that new theory was plate tectonics, which is the idea that the lithosphere, which is the crust and the very top skim of the mantle, all right, is actually divided into these rigid plates that are floating and therefore moving very slowly, very slowly. Some places maybe 8 centimeters a year, other places only maybe 1, 2, or 3 centimeters. Not all plates are moving at the same speed, but they're moving over time. And just for the record, yes, they have actually used GPS systems and measured precisely the locations, and they are moving. So they definitely are moving. Now, do we know for sure all about the convection currents? Are there things that we may not know about that? That is correct. If you see pictures of what the Earth looked like a billion years ago and how these different continents were together and go on one land and stuff like that, we can't always be 100% sure. Okay, and as we found more things, some of those fossils that originally said, hey, South America and these other places were together here, well, we've also found now some of those fossils other places where it wouldn't have made sense for them to be so much. So anytime you go back in time, and we're talking about millions, billions of years back, well, that stuff is a little more sketchy. But the plates are moving, and the best explanation we have is the convection currents in the mantle, which seems to fit with what we're seeing. And just like any model or explanation in science, we stick it with what we see occurring, and if it fits and explains things and helps us predict what would happen if something else happened, and then it turns out to be true, then we think, hey, that's a pretty good model, and that's kind of what we have. And the idea of plate tectonics explained a lot of things we couldn't explain before. For example, out in the Pacific Ocean, called the Ring of Fire, because if you start looking at all the earthquakes and volcano activity, there's a big old ring around the Pacific Ocean where this is happening all the time, and where there's a higher percentages of it. And now this would explain, if this were all one big Pacific plate, then at the edges here, you've got things running into it and pushing at it and whatever. And um, just like a war, where does all the action happen? Well, at the fronts, where people are hitting each other. Well, where these two plates meet, there's a lot of pushing and shoving going on, and that's where all the action, the volcanoes and the earthquakes tend to happen. Okay, and so this explained a lot of things about how earthquakes work. How did rocks become melted? Well, if they're being subducted down at the mantle, then you got this magma, liquid magma, and then if you it's hottest right there, so guess what? You had volcanoes and mountains forming near these. For example, we'll talk more about this when we talk about the different types of uh, convergent or divergent boundaries. But we have a lot of volcanic mountain ranges in the America. We also have down here in South America, we have the Andes. Okay, up here we have the Sierras and the Sierra Madres and all the different ranges, but they're all volcanic. We have Mount St. Helens and some of the Fort Hood, Mount Hood, and some of the other volcanic mountains along here. Okay, same thing down here in the Andes. We have these volcanic mountains that have formed and stuff. And so it made a lot more sense of why things work the way it does. It explained how the rock cycle came about, how it come we have magma being formed, why we have more magma that wasn't there before, why we have volcanoes um, showing up in certain areas and stuff like this. Okay, so it just made a lot more sense about how things worked. All right. Um, all right. Now, let's talk about three types of plate boundaries real quick, and then we'll be um, pretty well done for today. All right. We did talk, there are done a bunch of plates. Basically, we say there's 8 major plates. All right, and you can see those here. You have the um, South American plate, Caribbean plate, the Pacific plate, Australian plate. Notice it extends a lot bigger around it. You have an African plate and so forth. But then there's also an Antarctica plate, but there's also a lot of minor plates, and that's why you have those little ones that have extra activity areas around them. All right. All right. But like I said, where everything happens is at the boundaries of these plates. That's the front, if you will, where they are hitting each other and attacking each other. So let's talk about those first. All right, we have divergent plates. All right, or divergent boundaries. Okay. Divergent is where they're pulling apart. Okay, and that's kind of what we talked about up here. All right, as the let me see, let's talk about the magnetic, but all right, but you can see as it comes up, you have these convection currents going around and it pulls it apart. Okay, divergent means they're going apart. These are caused by what kind of forces? Tension forces, pulling them apart. And we've said, like I said, it's the convection of this asthenosphere or the upper mantle that's pulling them apart. All right. Yeah. Generally, when this happens, it's pulling it apart. There's going to be new magma coming up and creating new crust. All right. Um, it's relatively peaceful. You have this oozing magma kind of oozes up. It's not going to be explosive because there's no pressure building up and so forth. Um, and if it's in the ocean, then we get what we call the mid-ocean ridge because you've got this new magma coming up, making new rocks up here, making it higher, and that's why it tends to be higher. And we have that big, like the mid-Atlantic ridge running down the Atlantic Ocean. All right. On the other hand, on land, it pulls apart and the magma cools off quickly, and so we have what we would call a rift valley. All right. One of the more famous rift valleys is down here running through Africa. Okay, and it's pulling apart on land, then you have these rift valleys. Why? Because rather than pushing the thin ocean crust up and making the ridge like it does in the ocean, you have this thick continent. As the magma comes off, it cools off quickly, and so it's actually kind of lower. The Rift Valley in Africa is famous because where this magma has come up, you got high heat and pressure, which makes, of course, metamorphic rocks, but it also can create, if it's melted, of course, it would have igneous rock coming up, but diamonds, the high heat and pressure has created diamonds. That's why South African diamonds are well known because it's in this Rift Valley area. Okay, all right. Now that's divergent. Okay, they're spreading apart, make new crust, either oceanic crust or that in the ocean they make mid-ocean ridges because it's a thin crust, and as the magma wells up, it pushes it up and then cools off to make the ridges. On land, you get rift valleys. All right. Now, convergent means coming together. Come together right now over me, as the Beatles would say. But anyhow, you get the idea. All right. Um, all right. Oh, going back to divergent ones for a little bit. This is Africa over here. This is Saudi Arabia and stuff like that over here. We think a lot of these are pulling apart, and that is where the Red Sea has formed. And at some point, this may eventually uh, also going back down here, and some of this may break off and become a giant island. Now, once again, we're talking, in 4 or 5 million billion years, something like that. So don't worry about it, not happening anytime soon. But this is an example of some divergent areas where the African plate and the Arabian plate seem to be moving apart from each other. Okay, anyhow, so getting back to convergent. Okay, well, there's the. There we go. All right. Got all those for the other ones. Okay. Now, convergent. Convergent means if something converges, they're coming together. Okay. So here we go. Now, the difference is we have different kinds of convergent plates. Okay. We can have ocean to ocean. Okay. And that's kind of what we're showing here. If you have ocean to ocean, all right, like this one, you have an ocean plate and an ocean plate. When they come together, they're both dense and low, but eventually they hit. They're both going to be kind of pulled down, but probably eventually one of them is going to go under the other one, and it pulls, oops, it pulls the plate down. So you have this trench. That's one of the first characteristics of it. Okay, so you get this trench where it's forming, where it's pulling it down here. So you have a deep trench running here. But as this gets subducted, or you have a subduction zone, okay, we know the heat and pressure increases as you go down. So this oceanic crust begins to melt, and you have partial melting or magma welling up. Okay, if this magma comes up, then you have a volcano. That could be an underwater volcano, all right, in which case you have these underwater mountains or sea mounts, they're called, okay, and you have, if it gets high enough, eventually this underwater mountain sticks up and we have an island. An island is just a giant mountain, but just the tip of it that sticks up. So the Hawaiian Islands can be considered the Hawaiian Mountains. Okay, and they just actually stick up. Occasionally, we'll have a volcano that creates a new island or destroys an old island. Okay, blows the top off of it, and now it's underwater and it completely gone away. Okay, so and right along this area where you have all this subduction taking place, sometimes we call it a hot spot. Okay, now as if you have a hot spot, say right here, and as this crust moves over, if you have a hot spot, maybe it blows up a volcano here, and then it moves a little bit, and you have another one. A lot of times we have these what we call arcs, island arcs. Japan is this. I think you can probably see that one over here. Maybe Japan. You can see how it's kind of like a string of islands, okay, connected. Hawaiian Islands is similar. The Aleutian Islands up in Alaska, they just have these stream of it. And what we think is as the crust has moved over these hot spots, you get this little string of volcanoes, and it makes a volcano here, but then it moves over here, and then this hot spot makes another volcano. So you get this string or curved line of, or arc of islands, okay, volcanic island chains, and that's what created things like the Hawaiian Islands, Japan, and the Aleutian Islands up around Alaska. Okay, so that's ocean to ocean. So you get subduction, you get melted magma, therefore you get volcanoes, and the volcano very often, if they get high enough, can cause sorry, that can cause island chains. Okay, all right, that's ocean to ocean. Now, what if we have ocean to continental? it's the same thing. Let's keep going down here. Uh, there we go. Okay, so now we have continental. Continental is very thick, okay, very blocky. It's not as dense, but it's very blocky. And so if it's lighter and floats higher, we know it rises up higher. Isostasy, we talked about last time. Okay, when it hits the denser, lower ocean crust, the ocean crust gets pulled underneath it. And so, generally, the ocean is being subducted. Remember, the mid-ocean ridge is making new crust. Well, this is where we're losing the crust to make up for that. Okay, and so the ocean gets subducted. Once again, it begins to melt. As it melts, it can rise. Magma rises if it has two cracks, builds up pressure, and eventually may blow up as a volcano. And you have, guess what? A mountain change, just like the Andean Mountains in South America on this edge. As the ocean crust moves and gets subducted underneath that, you have these volcanoes and earthquakes that are related to that. Okay, and very often you see earthquakes over there. There's also the whole Andes mountain chain, which is built by volcanoes. We said that same thing happened in North America on the west coast. All right, and so, but once again, it's being subducted. So now you have a near continent trench. Okay, if you have ocean to ocean, that just occurs wherever that is, and therefore you can have deep trenches like the Marianas Trench that are out in deep ocean. But you also have some very deep trenches along the South American coast and along the North American coast where crust is being subducted. Okay, all right. But generally, you tend to have volcanic mountain chains along with it, and it tends to be near the coast. All right. The last one is, what if we have continental, continental? So this is what? Okay, we got continental crust, continental crust. They're both fairly thick. They're fairly blocky or thick. They're when they hit each other, it's hard for one of them to get pushed under the other. It may partially a little bit, but mostly they kind of run into each other and crumple. But when they crumple, they get higher, and so they get pushed up. Okay, and this is what we think happened in India, where we think it was on a separate continental crust at one time, and then it slammed into Asia here. And now they still keep grinding on each other, but since they're continent to continent, they can't really go anywhere, and they just kind of keep crumpling, which pushes up the mountains, which are the Himalaya mountains, Mount Everest, and that's why we think they're some of the tallest mountains that we have, okay, because they're continental. Now, because of this, you don't get subduction, so you don't have a bunch of volcanoes. You do get earthquakes, okay? Earthquakes can be fairly common, but it builds mountains. As it buckles up, it usually builds up the mountain range, but not a volcanic mountain range, just being literally shoved up into the air. Now, this also has a lot of heat and pressure associated with this, so as these push and shove on each other, they can create a lot of metamorphism. Okay, so a lot of metamorphic rocks are occurring in these continental. Now, a lot of people think that at one time, where we have the Appalachian Mountain may have been where two crusts came together, two continental crusts, and it built up the mountain range. But over time, we don't think there's any those continental crusts kind of fused together, and now there's not any pushing or shoving as much. So there's no mountain building, and over time they have eroded away, so that they're really not that big of a mountain range anymore as they probably were at one time. Okay. So that is continental volcano. You get earthquakes, but not so much with the volcanic activity because there's no subduction going on, no crust being destroyed or created. All right. The last kind is transform. There you can see where we think India and Asia were at one time. There was actually ocean maybe running through there, but as it got pushed up here, eventually India ran into the Himalayas, so your continental crust plus continental crust, and it lifted up to make the very tall mountains. Okay, now transform is kind of like the slip strike faults we talked about. It is where things are going side by side. Instead of one being shoved under the other, ramming into each other, they're going side by side. So you have plates that are moving. Okay, and this is what's happened out in California where the San Andreas Fault. All right, Los Angeles and this side of the fault is being moved up that direction. All right, and this side is moving this direction very slowly, but you can see in the picture over here how some of this mountainy stuff that should be over here kind of has shifted over. Okay, you can kind of see that. Okay, and that's because of the movement of the plate. Okay, and theoretically, if this keeps happening, eventually this stuff would end up out here somewhere and might eventually, Baja California and this part of California here might be completely surrounded by water. Once again, yeah, maybe a couple 100 million years or something like that. So don't worry about it anytime soon. Okay, now once again, these are strike slip faults. They slide going opposite direction. They catch and they build up pressure, and then they slip. And then when they slip, that's where you have the earthquake. Okay, that movement there. They're usually very fairly short, but they can be very strong. And the longer the pressure builds up on the slip fault before it slips, then the bigger the earthquake that can be expected once they do slip. All right. I said don't forget to watch the other lectures, but that's just kind of a quick summary of that. Sorry, we don't have any demonstrations. Can't take you to an actual earthquake or underwater to a subduction zone or the mid-Atlantic ridges, but that's just kind of the way it works sometimes. All right. All right. Don't forget to do your questions and take the quiz. And I believe we have a test coming up, do we not? All right. So let me double check. All right, don't forget your test will include chapter 16, which is radioactivity. That's kind of seems like I've been always back there, but make sure you do that. And then 25, which is rocks and minerals. 26, which was architecture of the earth, the crust and mantle, all that. And then chapter 27, which is the plate tectonics. All right. So get your questions done, take the quiz for this chapter, and then take your exam for all four. But together for exam number 3. The end is near. We're almost there. We're going to make it. Just hang in there. Have a great week.